In this lecture, we'll discuss some of the basic properties of the electromagnetic field. In the previous lecture, we have found out that in the relativistic theory, the electric and magnetic fields form parts or elements of the second rank tensor f alpha beta, which is displayed here. So one of the things that we'll be able to do based on this realization is figure out how the electric and magnetic fields transform under the Lorentz transformations. Now, before we get to that, let's first refresh our memory in general about the physical meaning of tensors, what they mean mathematically and why they're so useful in physics. Let's consider an example of a physical situation where a tensor naturally appears. Let's consider some kind of crystal. So let's say it's some material with some interesting crystal structure, and let's say it's a single crystal, and let's say it's metallic, and we apply electric field to it, so that because it's metallic, there will be some electric current in the material, so there will be some current density. We'll assume that the electric field is sufficiently weak so that the response is described by Ohm's law. So the current density is proportional to the electric field in the sense that if you multiply the electric field by a constant, the current is also multiplied by a constant. However, there is generally no reason in a crystal of a general structure for the current density to be collinear with the electric field. It can point at some angle with respect to the field, and the angle can depend on the orientation of the field with respect to the crystallographic axes. So linearity doesn't tell us anything about the directions. They may or may not be collinear. Now, what is a general form for a linear relation between two different vectors? So we have vector E and vector J, and we want a connection that is linear but is unrestricted in any other way. This connection has to be written for each component. So for example, Jx can be written as a linear homogeneous function of the components of the electric field. So we can introduce the material parameters sigma, xx, xy, xz that give this connection, and you can do this for the other two components too. Now, this can be compactified in the form of a matrix. So we write J as matrix sigma times E. This is the most general linear relation. The key point is that the components of vectors, J and E here, transform in a very specific way under rotations of the reference frame. And the object that connects them, so here it's the tensor sigma, has to transform in a way that's consistent with the transformation of the vectors. So this is essentially the definition of a tensor. It's something that transforms under rotations in such a way that the relation connecting vectors like that remains undisturbed. Let's see how this works explicitly. So first, let's recall the property of the matrices that generate the rotations in 3 dimensions. So let's say in reference frame K prime, we have vector J prime that is obtained from J through a rotation matrix R. So R is a matrix that depends on the rotation angles. So for instance, those could be the Euler angles alpha, beta, gamma, or there could be some other parameterization that doesn't matter. So it's a matrix that takes the components of J and gives the transformed components of J prime. Now, we know that rotations preserve the squares of vectors. That's what it means that the transformation is a rotation. So we should have j prime dotted with j prime equals j dotted with j. Now j prime is r times j. So we can rewrite this in the following way. So when we write j prime dot j prime, we don't think about the matrix structure of this expression because the inner product just multiplies every component of one vector with the corresponding component with the other. But if we want to be strict about this and stick to the matrix multiplication convention, we need to recall that when we multiply a vector by itself, so we are multiplying a row vector by a column vector. So this way the multiplication goes like this, row by column, and you get a scalar. Now if we use the conventional notation like j for a column vector, so this will be j, then this row vector is a transpose of j. So we could also write this as j prime transpose times j prime is equal to j transpose times j. It's the same notation, but it emphasizes the matrix structure of this expression. Now j prime transpose is j transpose times r transpose. The transpose of a product is equal to the product of transposes in reverse order. So if we substitute this in the expression telling us that the square of a vector is an invariant, we'll find j transpose r transpose r j equals j transpose times j. Now this has to hold for all vectors j, for an arbitrary vector j. That means that this matrix product here must be equal to the unit matrix. So r transpose times r is a unit matrix. This is the defining property of a rotation matrix. Now, how should a tensor transform under rotations? Now, I will explain that the proper transformation looks the following. So sigma prime ij equals r ik r jl sigma kl. So the same rotation matrices that act on vectors act on tensors too, but there's a separate rotation matrix acting on each index of a tensor. So rik, k is contracted with this k, and the result goes into the I index, and the second index is acted upon by the second R matrix. So JL and L is contracted with the second index of sigma. Why is it like this? How do we see this? Well, the first way to see this is to notice a special case. So here's a special case of a tensor. Consider some tensor, call it M, that is a direct product of two vectors, A and B. This symbol here designates a direct product, which is defined in the following way. The component of a tensor is equal to the product of components of vectors A and B. This is obviously a tensor because the action of tensor M on some other vector C is defined by taking the matrix elements AI, bj, and contracting the second index with the index of c. But bj, cj is just an inner product. So what remains is a times b dot c. B dot c is an invariant, and a is a vector. So m dot c is clearly another vector. So the direct product of two vectors represents a possible linear connection between the components of two different vectors. So it is a tensor. Now, the transformation properties of the tensor components should be the same for all tensors. So we can determine it from the transformation in this special case. We know the answer in the special case because we know that by definition m prime is a prime crossed with b prime. So if we write it in components, we'll find m prime ij equals r I k a k r j l a l. But a k a l is just m k l. So we have these two R matrices, and the structure of this expression is exactly like I wrote above for the sigma. So to find the transformation law for the tensor, we need to apply the rotation matrix R to each index of the tensor. If the tensor is higher than second rank, so if it has more than two indices, then there's an extra matrix R for each index. Also notice that the matrices we are dealing with, the R matrix, it's the same matrix that rotates the radius vector. So by definition, we can write it in the form that contains the derivative of the primed coordinates with respect to the unprimed ones. All these features of tensors remain valid in relativistic four-dimensional spacetime. We need to be a little careful though, because what is kept invariant by the Lorentz transformations is not the Euclidean distance, but the pseudo-Euclidean interval in four-dimensional spacetime. So let's say we have a four-vector A alpha. Now, to find its components in another reference frame, we call them A prime alpha, we need to apply the Lorentz transformation, which can be represented by a matrix. So let's write it in this way. Let's write it as L, upper index alpha, lower index beta, A beta. I want to keep the positions of the indices such that this expression looks as if it's a tensor relation. Now, you need to be very careful that L is itself, it's not a tensor, because it's a matrix connecting the components of vector A in one reference frame and another. So this is in reference frame K, this is in K prime. Tensors relate vectors in the same reference frame. So L is a transformation matrix. It's analogous to the rotation matrix in the three-dimensional discussion, but in itself, it's not a tensor. However, the placement of indices here is chosen so that we can easily keep track of who is covariant and who is contravariant for all the vectors that enter the expression. So here, the lower index beta is contracted with the upper index beta for alpha, and then what comes out is a contravariant vector. So here I have alpha as a upper index. Now, if I had a vector A written in covariant components, I would have a different transformation. So I'll have A alpha covariant written in terms of L with lower index alpha and upper index beta contracted with lower index beta on the A vector. So these are both Lorentz transformations, but one tells us how contravariant components transform, and the other covariant. Now, these matrices are different. They are not quite the same. They differ in some signs. Why is that? Well, this is because A alpha with the lower index is different from the one with the upper index. So they're connected by the metric tensor. We can easily figure out how the two different L matrices are connected. So to do that, let's write A prime alpha as G alpha beta A lowercase beta. And on the right hand side, I'll write L alpha beta and then substitute G beta gamma A gamma for A beta. So I took this expression and re-expressed contravariant components through covariant components. Okay? Now, we also know that G alpha beta G alpha gamma is a unit matrix. It's easy to check that this is the case. One can do it explicitly by looking at the components. So let's take this expression here and contract it with G alpha delta. On the left-hand side, I have G alpha delta, G alpha beta, A beta, and on the right-hand side, G alpha delta, L alpha beta, G beta gamma, A gamma. Now look at the left-hand side. So because of this relation here, the product of these two G's, so they're contracted by index alpha. This is just a Kronecker delta with symbols delta and beta. So I can remove these G's from here and replace beta by delta. And the right-hand side is what it is. Now, we also know from the definition of the transformation matrix that acts on covariant components that A prime delta must be equal to L delta beta A beta. Now, these matrices in these two equations, this one and this one, do the same thing. So it has to be the same matrix. We just need to be careful with the indices. So to make them the same on the right, let's replace this beta by gamma. It's a dummy index, so we're allowed to do that. And then we find that L delta gamma equals G alpha delta L alpha beta G beta gamma. Now G is a symmetric tensor, so I can also rewrite this as G delta alpha G gamma beta L alpha beta. So let's look at this expression. It looks like I'm lowering the alpha index using the G tensor as usual. So alpha index from here goes downstairs and becomes delta on the left. Now the second index, beta, is raised by this G and becomes an upper index gamma. So when we use this convention for L, where we place the indices so that it looks as if it's a tensor relation, then I can raise and lower indices for L as if it was a tensor using the metric tensors, even though it itself is not a tensor, but it makes the expressions quite convenient. Here's an example of the L matrices acting on contravariant and covariant components for the Lorentz boost in the x direction. So notice that when you lower one index and raise another, if the two indices are both space-like or both time-like, there is no sign change. But when one is time-like and one space-like, the sign reverses. So this term minus gamma v over c has an opposite sign in the two matrices. Notice that just as in the Euclidean space, we can write the definition of the matrices L alpha beta as the derivative of the primed coordinates with respect to unprimed ones. Now, in the Euclidean case, there's just one transformation matrix. In the pseudo-Euclidean, there are two, one for contravariant, the other one for covariant. So the covariant one will look the same, but the coordinates come with lower indices instead of upper. So earlier we saw that if in 3 dimensions vectors transform using rotation matrices, then second-rank tensors would transform like this, and similarly for tensors of higher rank. In Minkowski spacetime, the role of the transformation matrices, which were R in Euclidean 3D, is played by the Lorentz matrices L, which we just discussed. So we have a transformation for 4 vectors given by matrices L. In complete analogy with conventional tensors, which are defined in this way, tensors in 4-dimensional spacetime are defined using the L matrices like this. This is for the representation with contravariant indices, or for covariant indices, a similar expression. Notice that in 3D, in Euclidean space, there is no need to distinguish covariant and contravariant components. There's nothing like that because the metric tensor is simply a unit matrix. So in 3D, we could write Gij is just 1, 1, 1. That is the matrix that determines the square of a vector. So we have x squared plus y squared plus z squared. So it's diagonal and all elements are the same. So if you try to raise or lower the index, nothing happens. It's just a unit matrix. Now, in Minkowski space, we have to be careful about that. So here we have this novelty with upper and lower indices meaning different things. Now, they don't mean very different things. They, at most, reflect the sign change, at least in special relativity. That's what happens. But still, you need to be careful because those signs do make a difference. Now, the defining property for the rotation matrices that keep R squared invariant was that they are orthogonal. So we had an expression that looked like R transformed times R equals a unit matrix, or in components Rij, Rik equals delta Jk. Now, what is the corresponding relation for the L matrices? Well, the L matrices have to transform the inner product or the interval. So if we write an expression for A alpha prime A prime alpha, it has to equal A alpha, A alpha. Let's write this using the metric tensor and only contravariant components of vectors. And now substitute the L matrices. Because A is an arbitrary vector, we then have G alpha beta, L alpha gamma, L beta delta equals G gamma delta. Now let's raise the gamma index. I'll multiply by G gamma epsilon. The right-hand side becomes the Kronecker delta. Now, as we've learned before, one can simultaneously lower one index of the L matrix and raise another, and that would be the L matrix for covariant component of a vector. So this part here on the left, this piece, alpha is lowered and becomes beta, gamma is raised and becomes epsilon. So we have this expression. Let's condition the indices a little bit. We'll use alpha instead of beta, and beta and gamma for the remaining indices. The resulting expression is analogous to the expression we had before for the orthogonal matrix in Euclidean space, with the difference that now the two matrices entering here are different. The first one transforms covariant vectors, and the second one transforms contravariant ones. So let's check what happens when we contract indices in a tensor expression. From the point of view of its transformation properties under the Lorentz transformations, any tensor is equivalent to a direct product of vectors. So we can write some expression like A alpha, B beta, C gamma, D delta, and so forth, with various indices, some of which can be covariant and some contravariant. Now, if we want to see how a tensor like this transforms, so by the usual prescription that we discussed before, we need to act by the L matrix on each index. So if you want to write the components of this tensor, or this direct product, in the primed reference frame, so everything here is now primed, we're going to use the L matrices appropriate for each index. So for the contravariant indices, we use the corresponding L matrices. So first upper index, then lower index. And for the covariant index here, we use L appropriate for that case. Now, what happens if we decide to contract two of the indices? So we pick one contravariant and one covariant index. So here we can take gamma and something else, for example, alpha. So let's contract alpha and gamma. If we contract alpha and gamma, the indices alpha and gamma in this expression on the right will become identified. So then these two matrices will form a product that looks like L alpha mu, L alpha rho. But we've just seen that this is simply a delta symbol. So this is delta mu rho. So these two matrices, if we contract two indices, these two matrices will turn into a delta symbol, and it will generate a contraction on the right of A with C. So what remains is the product, direct product of B and D vectors that transforms as a second rank tensor does, we have a product of two L matrices staying there that acts on B nu and D sigma. So we have a tensor of a rank that is reduced by 2. This is the basic pattern in tensor expressions, both in Euclidean and pseudo-Euclidean space. Now let's come back to the electromagnetic field and see how the components of E and B transform under Lorentz boost. So we know the structure of the tensor containing the electric and magnetic field. For the boost in the x direction, the L matrix looks like this. So we can simply apply the rule to the field strength tensor and write that F prime alpha beta is equal to L alpha gamma, L beta delta, F gamma delta. This is the transformation rule for any tensor, so all we need to do is compute the sum. Now, for the Lorentz boost in the x direction, the calculation is quite simple because of the block structure of the matrix. So the y and z components are not affected at all, and x is only mixed with ct. So we don't really need to perform the full-scale matrix multiplication. First thing we can notice is that the lower right corner block of the matrix is not affected by this Lorentz boost at all. The y and z components of a vector are unchanged, so this block of a tensor is not affected at all. So bx remains the same under Lorentz boost in the x direction. So we can immediately write bx prime equals bx. Nothing happens to bx. Now, if we look at ex, so ex sits in this upper left corner. So this block is transformed by this 2 by 2 block. It's not mixed with anything else. Now, if we perform the multiplications, it's quite straightforward. The answer is that Ex also remains unchanged. So nothing happens to the field components along the direction of the boost. Now let's look at the y and z components. Here it's also quite simple. Because components 2 and 3 in the four-dimensional notation are not affected by the transformation at all, that means that the components of the tensor f02 and f12 transform as ct and x components of a vector. 2 is just a spectator, nothing happens to it. So only the L matrix that acts on the first index has an effect. Same thing for the components f03 and f13. So if we simply apply the transformation matrix L alpha beta, or rather its upper left block, this 2 by 2 block there, to f not 2 and f12, we'll find the f prime not 2 and f prime 12. Now f02 is the electric field component EY, and f12 is the BZ component. So these two transform through each other in the following way. We can write that the primed components minus EY and minus BZ go as gamma 1 minus V over C minus V over C 1 times minus EY minus BZ without the primes. Now there are primes everywhere, so we can drop the minus signs, and this will give us Ey prime equals gamma Ey minus V over C Bz, and Bz prime equals gamma Bz minus V over C Ey. Exactly the same happens with the components Ez and By, except that they're interchanged and there's a sign change there. So we can write Ez prime equal gamma Ez plus V over C By, and By prime equal gamma By plus V over C Ez. Now all of these relations by components, a total of 6 of them, can be combined in terms of a single vector expression for E and another one for B. First, let's notice that if the velocity is small, so that V over C is much less than 1, the right-hand side contains the velocity in 2 ways. The velocity enters explicitly in first order, and also through gamma, where it comes in second order. So at small velocities, we can drop the second order terms and obtain, in this approximation, E prime equals E plus 1 over C V cross B, and B prime equals B minus 1 over C V cross E. So I set gamma to 0, and then you can see that this expression correctly gives conserved longitudinal components, those parallel to V, and the transverse ones reproduce this. Now, if V over C is not small compared to 1, we can obtain the correct transverse components if we multiply the right-hand side by gamma. But then we will have an incorrect longitudinal components, because they shouldn't change, but if we multiply by gamma, it will change. So to fix that, we need to introduce a correction that fixes the longitudinal components. So generally, we'll have a more complicated expression. So for E prime, we'll have gamma E plus 1 over C V cross B, and then we subtract gamma squared over gamma plus 1 over C squared V dot E. And a similar expression for B prime. So for B prime, we'll have B minus 1 over C V cross E minus gamma squared, gamma plus 1 over C squared, V dot B. These expressions are written in a slightly different form in Jackson equation 11-149. We can make some useful observations based on these formulas. First, notice that the formulas apply at any space-time point. So the electric and magnetic fields transform through each other at the given space-time point. Now let's consider the case where in reference frame K, in the unprimed reference frame, the magnetic field to be 0 at some point. So at some time and coordinate. Then if we write the electric and magnetic fields in the primed reference frame, in K prime, we'll have E prime equals gamma E minus this term here, which is collinear to v. So it's some coefficient, let's call it a, v dot e. And the magnetic field B prime is equal to minus gamma 1 over c v cross e. Everything else vanishes because b is equal to 0. Now, in this case, we can write b prime as minus 1 over c v cross e prime. This is because v cross v is 0. So if we do v cross e prime, then only the gamma e term gives something not 0, and we get this b prime. Now, this means that b prime and e prime are orthogonal. So if in some reference frame magnetic field is 0, then in any other reference frame the magnetic field will be orthogonal to the electric field. Now let's consider another case. If in K E is 0 at some point, then in any K prime we'll have E prime equals 1 over c gamma v cross b, and b prime is gamma b minus same coefficient a v dot b. Now if we compare these two, we'll find that now E prime is equal to 1 over c v cross b prime. Again, the second term in b prime is destroyed by crossing it with v, so this is a correct expression. And again, we find that E prime and B prime are orthogonal. So it turns out that if there is a reference frame, if there is a reference frame K where either E equals 0 or B equals 0, then in any K prime we have E prime and B prime orthogonal to each other. But in addition to that, their magnitudes are different. E prime is not equal to B prime. This is because V over C is always less than 1. So if you take a B prime and cross it to a vector whose magnitude is less than 1, you will always get a vector with a smaller magnitude. Let us now discuss the so-called field invariants. These are the scalar Lorentz invariant quantities that can be formed from the components of the electric and magnetic fields. To form scalar quantities, we can take tensors and contract all of the indices. So for example, given that we have a tensor f alpha beta, we could, in principle, consider a combination f alpha alpha, a contraction of the tensor by both indices. But f alpha alpha is just 0 because the tensor is antisymmetric, so this doesn't give us anything interesting. So we can't form anything that's linear in electric or magnetic fields. Now the next thing to try is something quadratic in electric and magnetic fields, and to make something quadratic we need to make a direct product of tensor f with itself and then contract some of the indices. So let's see what we can accomplish this way. We can take a combination f alpha beta, contracting alpha and beta. Now, this quantity is in fact interesting. If we write out the components, so it's just a sum, reminder, the contraction is a sum of alpha and beta. So, for example, this will contain expressions like f01, f01 plus f02, f02, and so forth. You just sum up all of them. Now, remember that when we lower both indices, the elements of the tensor that have mixed time-like and space-like components, these are the electric field components here, change sign, and the fully space-like components don't. And otherwise, the covariant and contravariant components are the same. So wherever you have EX, there is an EX, and so forth. The sign is different for the covariant and contravariant for the electric field pieces, and it's the same for the magnetic field pieces. This means that this sum will give us minus e squared times 2, because there are two sets of components of the tensor. There are components here and components here, and each of them will give minus ex squared, minus ey squared, minus ez squared. That's minus e squared, and there are two of them. Now, the magnetic field elements will come with positive signs, because covariant and contravariant always have the same sign. So we'll have plus 2b squared. Now, this implies that b squared minus e squared is an invariant. It is a Lorentz scalar, which means it's the same in any reference frame. Now, what else can we do in second order? Here's one other thing that we can make that is quadratic in the fields and is also an invariant. Let's take the so-called fully antisymmetric fourth-rank tensor epsilon and contract the indices in this way. Epsilon is a fully antisymmetric fourth-rank tensor. It is defined in the following way. Epsilon 0, 1, 2, 3 is by definition equal to 1. And then it's antisymmetric with respect to all pairs of indices. That means epsilon alpha beta gamma delta is equal to minus epsilon beta alpha gamma delta minus epsilon alpha gamma beta delta, and so forth. An antisymmetric tensor cannot have any two indices equal to each other, because if you permute them, it has to change sign, but it doesn't, so it must be 0. Now, because of this antisymmetry property, it means that any element that is obtained by an even number of permutations of 0, 1, 2, 3 is equal to 1, and any one that's obtained by an odd number of permutations is minus 1. For example, epsilon 1, 0, 2, 3 is minus 1. So the total number of non-zero elements of epsilon is 4 times 3 times 2, that's 4 factorial, or 24. Of these, 12 are plus 1 and 12 minus 1. Now, in this sum here that we wrote, we need to figure out how to do the summation. Now let's focus on the sum over alpha beta. Once we pick the alpha and beta in the first factor, the gamma and delta in the second one are uniquely determined by the fact that alpha, beta, gamma, and delta should all be different. So we'll have terms like F01, F23, and so forth. And for each of the indices alpha and beta, there will be some complementary pair of indices in the second factor, but there will be two terms. There will be F01, F23, and minus F01, F32. But these two are actually identical because F itself is an antisymmetric tensor. Now, when we write down the components, we need to remember that these here are covariant indices, and this tensor here is contravariant. So everything that includes the electric field will change sign. Now, I'll leave it to you to carefully figure out which component goes with which. So for example, for the first term, F01 is EX, and with a plus sign because it's covariant, and F23 is minus BX. So we'll have minus EX BX. The electric field component always comes with the same component of the magnetic field. So if we sum this all together, we'll find this equal to minus 2E dot B. So E dot B is the second field invariant. Notice that E dot B is actually not a scalar, but a pseudoscalar. Whenever we form combinations involving the epsilon tensor, we get something pseudo. It's a pseudoscalar in the sense that it changes sign under spatial inversion. Indeed, B is an axial vector and E is a polar vector, so their dot product changes sign under inversion. And E dot B is also odd under time reversal. Field invariants allow us to make conclusions about the features of the electromagnetic field that are frame independent. For example, if the electric and magnetic field are orthogonal, if E is perpendicular to B in some reference frame, then this holds in any reference frame. Why is that? Well, because E dot B is a field invariant. So if it's zero in any reference frame. Similarly, if the magnitudes of E and B fields are equal in some reference frame, then this holds in any other reference frame, because E squared minus B squared is an invariant, and if it's zero in any reference frame. That means the magnitudes are equal. If the electric field is greater than B, it holds in any reference frame, because E squared minus B squared is positive. Same thing is if electric field is less than B. If E and B form an acute angle, then it's an invariant relation. That means that is because E dot B for an acute angle is positive. Same thing for an obtuse angle. We have noted previously that if electric or magnetic field is zero in some reference frame, then in any other reference frame they are orthogonal. This can also be immediately seen from the second field invariant. If one of the fields is zero, then E dot B is zero, and then it must be zero in any reference frame. That means they will always be orthogonal. The last thing I'll explain in this lecture is how two of the Maxwell's equations, those that don't have current and charge densities as sources, follow from the definition of the field strength tensor. Let's write down the definition of the F tensor with covariant indices. And I'm going to argue that this expression is an identity. Alpha, beta, and gamma here are three indices, and there are no contractions here. So there are three cyclical permutations of the same three indices. Now first notice that if any of the two indices here are the same, for example, if alpha and beta are the same, the first term is 0 because F is antisymmetric, diagonal elements are 0, and then the two other terms have the same dx alpha in the denominator, and in the numerator the two indices are interchanged in the two terms. So because of the antisymmetry of F, it's just 0, so that is not interesting. Now, in addition to this, there are four equations here where all four indices, alpha, beta, and gamma, are different. There are four ways to pick three indices out of four, so we have four equations. Now, first of all, let's prove this equation. This is quite straightforward. It follows directly from the definition of F and from the symmetry of the mixed derivatives. So if we just substitute the definition of F into this expression, this will give us terms that look like d2a beta, dx alpha, dx gamma, minus d2a alpha, dx beta, dx gamma. And the other two terms in this expression will contribute four more terms like this. And here, every term repeats twice with opposite signs. So with a beta, for example, this term cancels this, the term with a alpha cancels here, and the term with a gamma cancels. So everything cancels, and this whole thing is 0, which proves this equation. So let's try to parse it. We have four different combinations of alpha, beta, and gamma. Let's start with the one for which alpha, beta, and gamma are all space-like. So it's 1, 2, 3. Now, because the indices here in this expression are covariant, we need to change the sign in our F tensor here. So I'm going to do it now. And we proceed with this expression, setting alpha, beta, and gamma to 1, 2, 3. So here we have df 1, 2 by dx3 plus df 2, 3 by dx1 plus df 3, 1 by dx2. What is it? f1, 2 is minus bz, x3 is z. So here we have minus dbz by dz. Second term, f2, 3 is minus bx, differentiated with respect to x. So minus dbx by dx. The third term, f3, 1, is minus by. So you can see where it's going. Minus dby by dy. This is simply the negative divergence of b, which is 0, according to this equation. So the divergence of b is equal to 0. It's one of the Maxwell's equations, and it comes from this identity directly. What about the other three equations? Well, let's see what happens if we set alpha, beta, and gamma to 0, 1, and 2. So one of the time-like and two space-like. Here's the expression. So inserting the components of f, f01 is ex. So here we have dex by dy. f12 is minus bz. So we have minus dBz. X naught is CDT, so minus dBz by CDT. And the last term, F20, is minus EY. So we have minus dEY by dx. So here we have the same component of the curl of E and dBz by dt. Clearly, if we take two other combinations of 0 with two space-like indices, we'll have the x and y components of the same equation. So we obtain a vector expression curl of E plus 1 over c dB by dt equals 0, which is the other Maxwell equation without the sources. So we have two of these. This is one, this is the other, that follow directly from the structure of the F-tensor. This concludes this lecture, where we started with the general properties of tensors and then continued to discuss the features of the electromagnetic field that follow from its definition through the field strength tensor, and eventually making our way to the first pair of Maxwell's equations.